let's consider the vector space of functions. And the vector space of functions actually has an infinite basis. There are not a finite number of functions that spans all of the functions. We do not have a finite list of things that we could write every function as a linear combination of. However, what about linear independence? We still want to be able to talk about that. So let's think of something like sine x and cosine x. Before, you were linearly independent if I could not multiply the first one by a scalar to get the second one. So it seems like these should be independent, since I cannot multiply sine by a number to get cosine. But how can we show this? In order to talk about linear independence, we're going to define what's called the Wronskian. And for this, we need a square matrix. The first row, so row 1, is your functions. If I move down to the second row, this will be the derivatives of the functions. Row 3, if we need it, so if we only have 2 functions, we can stop at row 2. If we have 3 functions, we'll need the third row. This is your second derivatives. If you have more functions and you need a larger matrix, you can go to rows 4 for the third derivatives, 5 for the fourth derivatives, etc. These are going to be linearly independent if the determinant of this Wronskian is not equal to 0. So let's look at some examples of this. I'm going to start by going back to my example with sine and cosine. So to build my Wronskian, I'm going to put my functions first. So sine x and cosine x. And then the second row will be their derivatives. The derivative of sine is cosine. The derivative of cosine is minus sine. So these are my functions, and these are their derivatives. Taking my determinant, I have sine x times minus sine x, that's negative sine squared x, minus cosine x times cosine x, or cosine squared x. We could factor out a -1. We would have sine squared x plus cosine squared x. We know that sine squared plus cosine squared is 1, so this would be -1. So this would be linearly independent since we did not get 0. I now want to show linear independence of 1x and x squared. So my first row will just be these functions. My second row is the derivatives. The derivative of 1 is 0, derivative of x is 1, and derivative of x squared is 2x. Since we have 3 functions, we need the second derivative as well. Derivative of 0 is 0, derivative of 1 is 0, derivative of 2x is 2. So when I take this, I'm going to start by going down the first column. I have 1 times the determinant of, we delete that row and that column. We have 1, 2x, 0, and 2. And all the other terms in that column are zeros. So this is 1 times 2 is 2 minus 0, which is 2. So these would also be linearly independent since I did not get 0.